Okay, well, most of you were already convinced that the answer was B, which is the correct answer. Let's just go over it. Now, this is an example of, this just looks like the integral in the Gauss law. And the Gauss law states that if you take any closed surface, it doesn't have to be a regular surface, it doesn't have to be a sphere, it doesn't have to be a cylinder, it might have such weird shapes, whichever shape you like. Any surface, if you integrate the electric field over the surface, it gives you the total charge only inside the surface. It doesn't tell you anything about the charge outside the surface. It doesn't contribute to this integral. So E dot ds equal to 0 just means inside the surface there are no charges. It also doesn't tell us anything about how these charges inside the surface are distributed. So although this is satisfied, you can have configurations, for example, where you have some charge over here. If you have a single charge over there, this statement doesn't tell us that there cannot be any charge outside. There can still be charges outside. So if you put some charge over here, there will still be electric fields everywhere. So on the surface, the electric field is definitely not 0. Nevertheless, this integral is 0. Why? Because if you consider a surface element somewhere over here, if you take this surface element, let's say ds1, and if you take this surface element, ds2, now E at the point of ds1 is less than 0 because the angle between these two vectors are more than 90 degrees. And E dot ds2, this is larger than 0 because the angle between E and ds is less than 0, less than 90 degrees. So we have negative contributions from this side, positive contributions from the other side. The sum of all these negative and positive, they just cancel. Or you can just think of as the net number of electric field lines leaving your surface. Well, there is 1, 2, 3, 4. Here it is entering the surface, so it is -1. This is -1. This is -1. This is -1. 4 of them are leaving. 4 of them are entering. The net number of electric field lines leaving my surface is 0. E dot ds is again 0. This is one possible case where, although E dot ds is 0, the electric field on the surface is not 0. Similarly, you can also consider another example where, let's say, you have this plus Q charge, this minus Q charge on the other side. Again, the total charge inside, in this case, Q enclosed will be plus Q plus minus Q. It is 0. So again, by Gauss's law, I know that E dot ds on the surface over the surface is still 0. But nevertheless, we also know that the electric field lines of this configuration will look like this. So you see that some electric field lines do not touch my surface, whereas there are other electric field lines, like this one. They first leave the surface and then enter to the surface. The net number of electric field lines leaving the surface is again +1, -1, it is 0. But nevertheless, the electric field, the integral of the electric field over the surface is 0. Now, let's discuss one more concept and then we will go back to our discussion questions. Equipotential surfaces. Now we had already discussed the electric field lines, which allow us to determine visualize the shape of the electric field everywhere. Now the equipotential surfaces is more like, will help us to visualize the potential, the potential. How does the potential look like? I mean, usually when you are talking about the potential of a system, you don't draw figures like this. Usually the kind of figures you draw will look like this one. So let's say this is X, this is Y. You have one charge over here, let's say plus Q, another charge over here which will have minus Q. And we already know how the potential will look like. V at the point R will be 1 over 4 pi epsilon 0, Q over R minus R0, R1, minus 1 over 4 pi epsilon 0, Q over R minus R2, where this is at the point, let's say, R1, and this is at the point R2. Now again, how did we obtain this? We have a plus Q charge, so the contribution of the potential at an arbitrary point R of this plus Q charge is 1 over 4 pi epsilon 0, Q over distance of that observation point from this positive charge, and then we have this minus Q charge. The contribution of this one is 1 over 4 pi epsilon 0 times minus Q divided by the distance of the observation point from this charge. And as you see, the potential very close to this R1, the potential takes values that are very close, that goes to plus infinity. Very close to this minus charge, the potential takes values very, very close to minus infinity. So it takes all the values from minus infinity to plus infinity. Now, if you just fix one value of the potential, let's say you want to find all the points that have V is equal to V0, some value. All the points that have the same value. Let me define it like this. All the R for which V of R is equal to V0, this defines a surface. Now, the important thing about this surface is that at every point on this surface, we have the same potential. That's V0. This is what we call the equipotential. Now, the equipotential surfaces for this configuration will, for example, let's say the equipotential surface corresponding to a very large potential value will be close to the positive charge, so the equipotential surfaces will look like this one. This is how the equipotential surfaces for this configuration look like. Did you ever look at an actual map? Not the one, the Google or Google Maps. Yes, I saw something. That I saw something. You have these lines on the map which marks the points which are at the equal height. Now, these equipotential surfaces are just like that. They mark the points on this chart that have, here is not the height, but it's the potential. All these points on this line, they have the same potential. All the points on this line, they have the same potential. But it will, the points on this line have a different potential than this one. The potential value will usually also be written somewhere on these lines. But as long as you are on one line, all the points have the same potential. If you look at here, the potential changes very fast. So because you start from very large values here, we know that the potential goes to very small values over here. So the change is really fast. But we know that the change in the potential in a given length is nothing but the electric field. So this already tells us the magnitude of the electric field is larger when the equipotential surfaces are denser. So if you have more equipotential surfaces in a given length, the electric field in that point, at that point will be much, much larger. Well, it's usually, when you draw equipotential surfaces, you assume that the potential difference between surfaces have some fixed value. So we are assuming that the potential difference between any two successive lines have the same value. There are more lines here, that means the potential is changing really fast, but the change in the potential, delta V by delta D, is nothing but our electric field. Okay, here you see another line, another symbol that we use to mean that, okay, these two things are related somehow, they are proportional to. It's not an equality sign. I wouldn't put an equality sign here because this is, electric field is a vector, whereas the right-hand side, left-hand side in this form is not a vector, but they are just related, the magnitudes. So if you look at here, the change between this potential value to this potential value happens at a small distance, smaller distance than it happens over here. So it means that the electric field here is much larger than the electric field over there. Now another thing, well, at this point clear? I mean, what do we mean by equipotential surfaces? They carry exactly the same information as the electric field. Remember, in the case of the electric field lines, we could determine the direction of the electric field by just looking at the electric field lines, by looking at the tangent to those lines, and the magnitude was given by the density of the electric field lines. Again, the equipotential surfaces carry the same information, just a different way of showing the same information. The density is again proportional to the electric field's magnitude. And the only thing left is how do we determine the direction. But the direction of the electric field, you can determine from the definition of the potential difference. So if you remember how we define the potential difference is minus, well, let me write it like this. So if we have the potential at some point, P2, minus the potential at another point, P1, this potential difference is equal to minus from P1 to P2 E dot dl. Now, if we assume these P1 and P2 very close to each other, then we can just take this integral along the line that's connecting those 2 points, but since those 2 points are very close to each other, the electric field will be constant almost. So we will have this very small change in the potential as you move from P1 to P2 is minus E dot dl. This we had already discussed on Thursday. So if P1 and P2 are on the same equipotential, if they are on the same equipotential, it just means that the potential difference between those 2 points is 0. But that means that E dot dl is equal to 0. And also remember, this dl is a vector that connects the position of P1 to the position of P2. Since both P1 and P2 are on the equipotential surface, this dl is a vector that is tangent to our equipotential surface. And for any dl vector tangent to our equipotential surface, this has to be 0. But this just means that E and dl are perpendicular to each other for any dl on the surface, E is perpendicular to the surface. So this also tells us the direction of the electric field lines. So if you know the equipotential surfaces. So in this case, these are the equipotential surfaces. The electric field lines will always be perpendicular to the surfaces. Now if you just go perpendicular to all these surfaces, these will be the lines that you will obtain. These are nothing but the electric field lines that we had derived. We had the electric field lines of a dipole. So if you know the equipotential surfaces, from that information you can also derive the electric field lines or the electric field vectors themselves. Okay. So what is field? Field. So what is this field? Now this electric field is nothing but a function that assigns a vector, so-called the electric field, electric vector, at every point. So a field, you can think of it as a collection of vectors. So it's just a function. So for example, it's a function whose arguments are points in space. So for example, I can just take this point over there, and the electric field just defines a vector at that point. And in this case, that vector will point somewhere like this. This will be the direction of the vector that the electric field defines at that point. That's just a definition, a terminology. No. Okay, so it's not in the radial direction. This is the radial direction. Other questions? The infinite plane. Example. So we had already discussed this infinite plane which carries some uniform charge density, let's say positively charged. We already know the electric fields. How does the electric fields look like? It's horizontal, parallel, uniform. So these are the electric fields. Okay, equipotential surfaces have to be perpendicular to the electric fields everywhere. So the equipotential surfaces have to be perpendicular. These are my equipotential surfaces. And since the electric field is uniform, the equipotential surfaces should also be uniform. Because we said that the density of the electric equipotential surfaces is proportional to the magnitude of the electric field. If you know the equipotential surfaces, by just drawing lines perpendicular to those surfaces, you can determine the electric field lines, and you can go the other way around. If you know the electric field lines, just draw surfaces that are perpendicular to those lines everywhere. That gives you the equipotential surfaces. Other questions? Now we will just consider a positive charge. A positive charge moves from larger potential, no, let's say towards smaller potential and smaller potential energy, smaller potential, larger potential energy, larger potential, smaller potential energy, and larger potential, larger potential energy. Which one is true? Now first, think about it. Again, A, B, C, D. This time we will have four groups. One group will gather here, A group. B group will be on the corridor over there. Group C will be on the corridor over there. And group D will be over here. No, you have to choose an answer. A, B, C, and D. You can take your time to discuss with your friends. Now, when I say that it will move towards a smaller potential, just understand that it's at a point where the potential is larger. It will just move towards a place where the potential is smaller. Okay, I want everybody up eventually, within this hour. Now, I have a region of space where I have a non-uniform potential. I have this charge. It moves in a given direction. So it will accelerate towards a given direction. So the question is asking if it is accelerating towards a region where the potential is smaller, potential energy is smaller or larger. There are, of course, other charges in the universe which is creating this non-uniform potential distribution. For example, you can assume that it's a proton. You have a free proton somewhere over here. Group A, Group B, Group C, Group D. I want everybody up. B is over there. Group B upstairs in the corridor. I don't care about whether the speed is constant or not. I only want to know is the direction of its acceleration. A, B, C, and D. A is over here. I will start asking questions to the ones who are sitting down. Yes, make your choices. Everybody should choose A, B, C, or D. You also have to make a choice. A, B, C, or D. C. C is over there. Okay, nobody thinks it's D. Okay. Now, I'm not saying there are no other charges. There are other charges who are creating this potential somewhere else in the universe. I have a single, I'm looking at single positive charge, and the question is whether this single charge, will it move towards a lower potential, higher potential, lower potential energy, higher potential energy? Volunteers, YA? Somebody else? Somebody else? Somebody who didn't speak before? No? Okay. No. They should hear. No.
Yani pozitif ve negatif yüklü elektrik oluşturan iki tane hani şey düşünsek. Artı Q burada olur mesela. Artı Q buradan buraya doğru gidecek. İvmelenecek, hız kazanacak. Hız kazanacağı için kinetik enerjisi artacak. İşte potansiyel enerjinin konumundan potansiyel enerjisi düşecek. Ve artı yükte potansiyel high potential olduğu için hani low'a geçmiş olacak. İkisi smaller olacak o yüzden.
Okay, there's one explanation over here. She wants to think of two parallel plates, and she says that, okay, I have this positive plate, this negative plate. If I imagine a positive charge close to the positive plate, it will accelerate towards the negative plate. Its kinetic energy is increasing, so its potential energy of the system should be decreasing. So she says that the positive charge moves towards in a direction which lowers the potential energy. And the positive plate has a larger potential than the negative plate. So she says that as the proton is moving towards the negative charges, the positive charge is moving towards negative charges. It is moving towards a region which has a lower potential. So both the potential energy is getting smaller and the potential is getting smaller. The potential at the point where my positive charge is. So that's her explanation. Any objections to her explanation? Why do you disagree with her? Okay, if you agree with her, you should move here. If you are staying there, that means you disagree with her. So why do you disagree? So you are also saying that it goes towards smaller potential. But you just said that it's moving from the positive plate to the negative plate. Positive plate has larger potential. That is what you said, no? So it is moving towards the smaller potential region. C is, it says it moves towards a larger potential region. Yes. Yes. That is what C is saying. It goes from the smaller to the larger potential region, from a large potential energy to the smaller potential energy. That is what C is saying. So if you are claiming that it is moving to a region of smaller potential, then it is either A or B. That both A and B is saying that it moves towards a smaller potential region. Okay, so group C is almost eliminated. Okay, we have another objection. So you are also saying that if the charge is accelerating, that means it's going to a region of smaller potential energy. So it is, you are saying either A or C, both of them are moving towards smaller potential energy, but you are also claiming that it is moving towards a larger potential. It is at rest. The positive charge starts from rest. So why does it go towards a larger potential region? It goes to smaller potential energy, but why larger potential? No, the potential energy is decreasing. Both A and C, it's saying the same thing. Potential energy is decreasing. But potential and potential energy are two different things. They are not the same thing. They are related, but separate objects. Okay, any answer from part B? So why B? Okay, any volunteers why you think it is part B? Okay, they are contemplating. So anybody who would like to try to convince them? Okay, you can start to think about what happens when if the charge is negative. Will the answer be the same or will it be different? That will be the next question. With the same choices. Okay, hold on. Okay, any explanation why it should be B? Why should it be B? Yes, B. Why do you think it is B? The negative plate has a larger potential? Smaller potential, okay. So you are saying it's either A or B. Both say that it's smaller potential, but you are also claiming that it's moving to a larger potential energy. Now, let me just clarify one more thing. When I'm talking about the potential, I'm talking about the potential at a given point. When I'm talking about the potential energy, I'm talking about the potential energy of the whole system. So as the charge is moving, is the potential energy of the system decreasing or increasing? Smaller means as the charge is moving, the charge will try to move in the direction such that it will try to decrease the potential energy. That is what I mean by smaller potential energy. Or if the charge is moving in a direction which will increase the potential energy of the system, that is what I mean by the larger potential energy. How going to a region of larger potential energy will decrease the potential energy of the system as a whole, including my positive charge? The system is everything, including my positive charge. The potential is the potential created by all the other charges. No, the potential energy is the potential energy of the whole system, everything. So you are A now? You are A person or... Yes, others. Why B? Any explanations? Why do you think it is B? Okay, any explanations why you think it is C? Okay, so you are over there now. Why B? Well, let's go back to your seats. We will discuss it. Okay, now let's start with the potential energy. Now, the potential energy in general, whichever kind of potential energy you are talking about, whether it's the gravitational potential energy, electrical potential energy, spring potential energy, any potential energy, is defined in such a way that the system will always try to minimize the potential energy. It will always move in the direction which will minimize the potential energy. Now, in this case, well, that basically, for me, is enough to say that it always goes to smaller potential energy. Let's also prove it in a more formal way. You see, we had defined the potential energy at a point P, or now the potential energy difference between 2 points we had defined as the work that we have to do in order to create the final configuration. That is how we define the potential energy. So if you leave this positive charge over here, if you let it go, it will just move in this direction. Let's say in some direction. Positive charge starts from here, it moves over there. It tells me that there is a force in this direction. So if I want to create the initial configuration, I have to take the positive charge from here. I have to exert a force opposite to this existing force so in order to move it back into its initial position. That means if I take this charge from here and move it over here, I am doing positive work. Well, the potential energy difference is the work that I have done. So the potential energy difference, if I take this charge from its final destination to its initial destination, I'm doing a positive work. It means initially it had a larger potential energy than finally. So it always goes to a lower potential energy. Now, the force that the positive charge feels is in the same direction as the electric field. Instead, if I replace the force by the electric field, I calculate the difference in the potential. Remember the definition of the potential. The potential, let's say the potential difference is nothing but the potential energy difference divided by the charge. But since we are talking about the positive charge here, the sign of the potential difference and the potential energy difference is the same. So since the positive charge goes to a region where the potential energy is getting smaller, the potential difference is less than 0 if you take the final potential energy minus the initial potential energy. The same holds for the potential difference. Or you can just look at the definition. Remember, delta V is minus E dot dl. This is my positive charge. Since it is accelerating in this direction, I'm just assuming that it's moving in this direction, it means that the electric field at that point is pointing in that direction. So if I start from here and move to the final point in this integral, E and dl will be in the same direction, so E dot dl will be positive. So delta V, which is the potential at this point minus the potential at the initial point, will be negative. So also from the definition you can see that if you take a positive charge, it always tries to go, let's say, from a larger potential to a smaller potential. It will always try to minimize the potential energy of the system. Now, if you consider a negative charge, so the answer in this case, it goes to a smaller potential and smaller potential energy region. Now, instead of a positive charge, if you took a negative charge, so let's say the same question, but we don't have the positive charge. We have a negative charge. It will always go to a smaller potential energy region, whatever the charge is. Whatever the system is, the system will always try to minimize the potential energy. So it will always go to the smaller potential energy region. So the answer is still either A or C. But since this time it's a negative charge, and the potential difference is the potential energy difference divided by the negative number. Since the potential energy difference is negative, the potential difference is positive from the initial to the final point. So it goes to a larger potential region which has a smaller potential energy. Again, if you think of the analog of these two parallel plates, in the two parallel plate example, if you put the negative charge close to the negative plate, it will accelerate towards the positive plate. That means its kinetic energy is increasing, But it also means that since the energy is conserved, the potential energy of the system should be decreasing. So again, the potential energy will get smaller, but since it's moving from the negative plate, which has a negative potential, to a positive plate, which has a positive potential, the potential is getting larger. It is increasing. Although the potential energy is decreasing, the potential is increasing. So that's mainly the main difference between a potential. I mean, this exercise, let's say, just emphasizes the fact that potential and potential energy are related but different things. For potential energy, you can always say that the system will always try to minimize the potential energy, but you cannot say the same thing for a potential. Yes? Potential energy or potential? Potential energy. Yeah, you cannot really talk about the potential energy in this region. The proper way is the potential energy of the system. So you're asking, if my charge is in this region, the system will have a larger potential energy than in the other system. Okay? Continue with your question. Okay. No. I mean, if it goes to a larger potential energy region, the potential energy of the system is increasing. Maybe you are thinking that if it goes to the larger potential energy region, it will extract the potential energy from the rest. Is that what you are really thinking? No, but the potential energy is a property of the whole thing. I mean, it's not the potential energy of my charge and the potential energy of the rest. It's the potential energy of everything. So if you're, and I mean, as the object is moving, I mean, the thing is, you cannot really assign the potential energy to a region. It's the potential energy of everything. I can talk about the potential, electric potential at a given region. But that would mean, if I put that would just tell me how much potential energy my whole system will have if I put my charge over there. So it doesn't really make sense too much sense to talk about the potential energy of my charge being in this region or in the other region. So it's always the potential energy of the whole system. Now you can just think of it as, I mean, an object falling down. As this is dropping down, the potential energy of everything is getting less. The object is going to a smaller potential energy region, smaller potential energy configuration. Okay, then see you on Thursday. Bring your questions on Thursday.